Now, when we look at the factors that affect the equilibrium position, we need to understand what I mean by the equilibrium position. The equilibrium position is simply the place where we talk about whether, once the chemical equilibrium has been reached, whether it means that we have a lot of product at that point or whether we have a lot of reactant at that point. And we can change that. We can push the equilibrium. We can make it want to do different things, okay? So when we talk about the position, this is what we're going to look at now. We're going to use a very important principle, and it's known as Le Chatelier's principle. It's very, very important. And it says to us, when the equilibrium in a system is disturbed, okay, so we do something to disturb the equilibrium. We'll talk about that. Now we change one of the conditions at which the equilibrium was established. A new equilibrium will be reinstated by favoring the reaction that does the opposite to the disturbance, okay? So it's pretty much like woman, okay? We're going to put it out there, like a girl. Never happy, okay? You do one thing and she wants the other thing done. When it's hot, she wants to be cold. When it's cold, she wants to be hot. Think about when you come into my classroom, or you go in summer, you walk into a room and you want the aircon switched on to make it colder. In winter, when you walk into a room, you want the heater switched on because you want it hotter, okay? So you want the opposite of what you're experiencing, and this is exactly what happens with the equilibrium, okay? So when we talk about the forward reaction being favored, it means that I'm going to make products. That's what favoring the forward reaction means. The rate of the forward reaction will be greater, so it's going to start off faster, and then the rate of the reverse reaction, and the reverse reaction has to catch up. The concentration, remember, that means concentration of the products will increase, and the concentration of the reactants will decrease. We make products when I say I favor the forward reaction. If the reverse reaction is being favored, then the rate of the reverse reaction gets bigger for a little while, and the rate of the forward reaction is slower, and the forward reaction has to catch up. That also means that with this process, we're going to make the reactants. So, I'm going to run out of space. The concentration of the products will decrease, and the reactants will increase. So now we've got to look at how this happens. There's several things we can do, and the first one is concentration. So here we have a reaction with a cobalt chloride ion, which is blue, in water, and a COH2O62 plus ion, which is pink. You don't need to worry about where we get them from, but we have this cobalt chloride substance, and we dissolve it, and we get this nice blue, and they're very distinctive colors, okay? If my reaction goes blue, it means I have lots of reactant because the reactants are blue. If the system is pink, it means I have lots of product because the products are pink, okay? So now we're understanding how the two go. So if I add in water, I'm adding in this. Your system, that's the disturbance. The system doesn't like the fact that you've added in water. So what must it do? It must use up the water, and the only way it can do that is to make product. Alright, so adding water makes more water available in the reaction. The forward reaction will be favored to use up the extra H2O, so my solution will turn pink because I have lots of product left. Alright, next one. If I add HCl, now here we've got to be careful. There is no HCl in my original reaction, but hydrochloric acid will ionize and become H plus ions and Cl minus ions. When I look at my reaction, I go, oh wait, look there, I have Cl minus ions. So what I've actually done is I've increased the concentration of the Cl minus ions indirectly. So the HCl increases the Cl minus ions, okay? Therefore, the reverse reaction gets favored to use that up. So I want to use it up. How do I use it up? I make reactants, so the solution turns blue. So if I add something in, I need to use it up, okay? Whichever way helps me use it up. It's also known, this process is known as the common ion effect. if I add silver nitrate, now this is a very big MB one, very important, silver nitrate, okay? Silver nitrate, when it dissolves, becomes silver plus ions and NO3 minus ions. The silver plus ions then see the Cl minus, so they see that, and they go, oh, I like you, and they make silver chloride. The problem is that silver chloride is insoluble, okay? So the silver chloride comes out of the system. So what we've actually done by adding the silver nitrate is we've found a way to get the chloride ions out of the system, okay? So adding AgNO3 decreases the concentration by forming the insoluble AgCl, okay? The forward reaction must then be favoured in order to make more AgCl, to make more of the Cl, okay? Because that's what it wants. Therefore, my solution turns pink. So if I add something in, it needs to use it up. If I take something out, it needs to make it. Okay, very, very, very important. So, what about pressure? Now, pressure only affects gases. So there has to be at least one gas particle in the system. If there are no gases, then pressure is irrelevant. If we look at the following reaction. So we have N2O4 going to NO2. N2O4 is colorless. NO2 is a very dark brown gas. Okay. Now, if I increase pressure, what you have to remember is that pressure is defined as the number of collisions per unit area on the sides of a container. Okay? Per unit area on the sides of a container. So it's all about the number of collisions. If we increase pressure, we've made lots of collisions. So what does it need to do? It needs to decrease the pressure. How does it do that? It has less collisions on the container walls, which means I need fewer particles. Increasing pressure, it shifts to decrease it. How does it do that? It must favor the reaction which has the least number of gas particles. I don't care about the size of the particle, I care about the number. There's only one gas particle over here, and there are two over here. It's going to want to go to this side because there's less. So the reverse reaction is favored, and the gas turns lighter brown. Note I haven't said colorless. Why? Because there must always be NO2 present in the reaction. Always. You cannot get around this. Okay? When we have a decrease in pressure, we need to have something that happens that will then increase the pressure. How do we increase the pressure? By favoring the side of the reaction that has the most number of reactants, or most number of particles, right? So decreasing the pressure in equilibrium will shift to increase the pressure. Increasing the pressure favors the reaction which has the greatest number of gas particles. So the forward reaction is favored because there's the biggest number, and the gas turns darker brown. All right. Temperature. Temperature is like switching the heater on or the air conditioner. Okay. So when we look at the reaction, okay, and here we've got delta H. This delta H is very important. With temperature, I need to know if the forward reaction is exothermic or endothermic. Delta H being less than 0 always, or any delta H, always refers to the forward reaction. Now, delta H here is less than 0. What does that mean? That means that the forward reaction is exothermic. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Exothermic gets hot. Endothermic gets cold. So exothermic is like putting the heater on. Endothermic is like putting the aircon on. Let's look at what happens. If I increase, there we go. If I increase the temperature, the equilibrium will shift to decrease the temperature. And in the case of the reaction that we're looking at. So here, the left side is endothermic, the front is exothermic. So if I'm favoring the reverse reaction, it's going to go blue. If I decrease the temperature, it's going to favor the forward reaction because that's the exothermic reaction, because that increases the temperature again. Okay, now very important. An increase in temperature increases both rates. A decrease in temperature decreases both rates. So in other words, when I increase temperature, when equilibrium gets reached, the rates will be faster than they were before. If I decrease the temperature when equilibrium is reached, they'll be slower than before. Now, what does a catalyst do? Here you need to be very careful because this is where they're going to catch you. A catalyst cannot favor the reverse or the forward reaction. There's absolutely no way it can do that. Okay? A catalyst does not affect the equilibrium. It only increases the rate at which equilibrium is reached. It'll only get there faster. Okay? Very, very simple. Now we're going to do a little bit of summary, and I know we've done a lot in this short period of time, but when you practice this, it gets better. So if we look at the summary, with concentration, if I increase the reactants, I need to favor the forward reaction to use them up. If I increase the products, I need to favor the reverse reaction to use up the products I made. If I decrease the concentration of the reactants, I'm taking reactants out, then I'm going to favor the reverse reaction in order to make the reactants that I've just used. If I decrease the concentration of the products, okay, then I'm going to make product. Very simple. Now these are nice because these you can learn. These are always the same. Be careful with the next ones. With temperature, if I increase temperature, I must favor the reaction that is endothermic. So I have to be able to work out whether the forward or reverse is endothermic. When I lower the temperature, I will favor the exothermic reaction. Very, very, very important. If I increase the pressure, I must favor the side with the least number of gas molecules. If I lower the pressure, I must favor the side with the most number of gas molecules. Okay? So, consider the following equilibrium reaction, and then they ask what would be the effect on the equilibrium system if CO2 is added. I'm putting in CO2, so it needs to use it. I'm going to favor the forward reaction. So concentration of CO2 is increased. The forward reaction is favored to use up the extra CO2. The forward reaction will be favored. Okay, you don't actually need that. I don't know why I put that twice. Okay, but this is what's going to happen. If I add CO to the system, it's going to want to use it up, which means we've got to favor the reverse reaction. So the concentration of the CO is increased. The reverse reaction is favored in order to use up the extra CO. Okay? Great. H2 is removed. Well, if we go back to the reaction, H2 is one of the reactants. If I take out a reactant, then I'm going to favor making it. So, concentration of the H2 is decreased. The reverse reaction is favored to try and make more H2. When H2O is removed, well, H2O is removed. The forward reaction is favored to try and make more H2O. Very, very simple. Consider the following equilibrium reaction. So now we've got the making of SO3. What would be the effect on the equilibrium position? In other words, are we going to make more reactant or product if the temperature in the container was increased? Well, delta H is negative. That means the forward reaction was exothermic. I've increased the temperature. It's got to favor the endothermic reaction, so it's going to favor making reactants. So the reverse reaction is favored. The temperature is increased, the equilibrium is adjusted to decrease the temperature. Quite simple. And that this means the reverse endothermic reaction is favoured. What would be the effect on the equilibrium position if the temperature in the container was decreased? Well, the forward reaction will be favoured because the forward reaction is exothermic. Temperature is decreased. The equilibrium is adjusted to increase the temperature. Therefore, forward exothermic reaction is favoured. Alright. Consider again the SO3 reactions with gases. If pressure is increased, so now I look at this and I go 2 plus 1, 3 gas particles, 2 gas particles. I increase the pressure, which means it's going to go to the side with the least number of particles. So it's going to favor the forward reaction because it's got the least number of moles of gas. Alright? Very, very simple. If I decrease the pressure, it's going to go to the side with the most number. Now, I need you to be paying attention to how we've written the answers because that's quite important, okay? The reverse reaction is favored. A decrease in pressure will favor the reaction that produces the most number of moles of gas. Thus, the forward reaction is favored. Lastly, and this is quite important because this is where they're going to trick you, consider the following equilibrium reaction. And then they say, suitable catalyst. What does a catalyst do? Catalyst speeds up the reaction. Equilibrium is not affected. It just means that it's going to get there quicker. You now need to please do activity 3 on page 232, questions 1, 3, and 4. The answers, the memos are in Teams.